The first part of the trig functions, though, actually has more to do with finding the area of circles and things like that. It's actually part of the 2-unit course, but it does come into play, obviously, in some practical application. So it's not like you can just neglect it and go, oh, 2-unit, don't worry about that. It's certainly, there's been 3-unit problems and 4-unit problems that use this idea. Radians, though, a reminder about the radian measure. And there's our conversion. I mean, pi is 180, but I always think of it as 360 as 2 pi, because I think of 360 as a circle, and I think circumference of a circle, 2 pi r. So I can readily associate 2 pi and 360. So that's how I tend to remember. But radian measure becomes very, very important when we do get onto looking at calculus. We need to be using calculus as the angular measure for it all to work. So we tend to get, and you saw when we looked at complex numbers, also then we gave the argument in terms of pi. We gave radian answers rather than degree answers. So arcs and sectors, there's a good old circle. We know, of course, yes, circumference is 2 pi r and area is pi r squared. Now, if I just wanted to find there's our sector. So AB would be a minor arc. Of course, there's a major arc the other way as well. But I only want to find the length of that minor arc. Well, I can do it via the ratio of the angle at the centre. So the angle at the centre is theta, and this is why we use radians. Because if I'm talking about radians, I divide by the total angle of the circle, which is 2 pi. The 2 pi cancels very nicely with the formula 2 pi r, so we get a really neat formula, just radius times the angle. But that angle needs to be in radian measure for the formula to work. So length is equal to r times theta. It's similar with area. We just do the proportion. The pi cancels, and we get a half r squared theta. Half r squared theta. But again, once again, that theta needs to be in radians for it all to work. So, okay, let's just do an example. And of course, I've purposely put it there in degrees, just to highlight the point that 45 degrees is no good to me with these formulas. So r theta, I don't substitute in 45, I substitute in pi and 4. 45 degrees is, of course, pi and 4 radians. So the exact length would be 5 pi on 4 centimetres, which, of course, as mathematicians, we're certainly happy with that answer. Science teachers would be uncomfortable. They go, 5 pi and 4? How on earth do you measure 5 pi and 4? Where's my ruler? Where's 5 pi and 4 on my ruler? Half r squared theta for the area, and we get 25 pi and 8. 25 pi and 8. Another question I like to ask is finding the area of not the sector, but the segment. So if I just chop the segment, there it is there. Again, there's the minor segment. The major segment would be the other part. And, well, how we can do it? Well, we've just found the area of the sector. We just take away that triangle that's inside. Some people like to remember the formula, because it's always going to be half r squared theta minus formula for the area of a triangle, half AB sine theta. But A and B in this case, of course, are both the radius. So you also get half r squared, common factor. So theta minus sine theta. That's up to you if you want to remember another formula, or you just derive it each time by remember, oh, yeah, sector minus triangle. Substituting in, that's a wonderful answer. Our science teacher has now collapsed. But we're more than happy to accept that as an answer. 25 pi root 2 minus 100 all over 8 root 2 centimetres squared. All right, well, that's it really for today. And we'll start on the trig functions proper on Monday.